Okay, thank you. So welcome to this session on the last day. So first of all, I would like to thank the organizers for inviting me to give this presentation and also to spend this week here. Presentation today will be different compared to the presentation we had so far. The reason that I'm a geophysicist, I'm not a mathematician, but I'm interested in inverse problems, and I shall give you some illustrations or some examples of inverse problems. So when I was preparing the presentation, I thought we work in different communities, in medical imaging, in geophysical imaging, so I thought it's maybe nice to also give you opportunities to learn more about geophysical jargon or geophysical terms and what we do, what we mean by seismic imaging, what we mean by seismic migration, and so on. So if you are a geophysicist, then the beginning of the talk is very easy, very simple, and for others maybe it is an opportunity to learn more about what we mean by seismic imaging. So let's start with very simple things. Here is our observed data, an image of observed data. So the vertical axis is time. So we record signal through time, where we have an active source somewhere on the surface, and the horizontal axis is sensor position, so the receiver position. So the source is around here, and we have negative and positive, what we call offsets. That is the distance between the source and the receiver. So basically we do not record anything here, simply because a wave has a limited velocity, so it takes some time for the wave to reach different sensors. So what kind of sensor do we have? In marine data, we have sensors sensitive to pressure changes, so we have hydrophones. And in land acquisition, we have sensors sensitive to little displacement. So we have what we call geophone sensors. Okay, so the objective is from this type of records to determine the Earth structure. And here we would like to determine the P velocity structure, the S, the shear velocity structure, or maybe also density. Or you could use alternative formulations with Lamé parameters and density and so on. So how to do that? Well, there are plenty of possibilities. First thing is just why not trying a given model. So suppose I have a very simple model consisting of two parts with a single interface. So velocity above is a constant at 2 km per second. Velocity below is higher, but also homogeneous. And I have one interface in between, and I have a little scatter points here. So is it a good model to explain this data? Well, not. Well, but how to know that? Well, we simply have to solve the wave equation for the source position, somewhere buried here. And if we do so, then we would compute synthetic data similar to this one, where we could observe source position here, recorded time and receivers, where we have direct arrival, so the basically arrival traveling along the surface. We have this kind of shapes, hyperbolic shapes in this here, where we have reflected data, and here also some sort of hyperbolic shape related to the scatter points. And if you have good eyes, or if you come to my screen, you also could see that you have interferences here between the scatters and the reflection part, so between these two singularities, where we call that multiple scattering. Okay, so this is not a good model in the sense that we have large misfit between this and this. So how to do in practice? Well, we have to find a methodology, automatic schemes. In fact, it's a difficult problem. It's a highly nonlinear problem and ill-posed problem. The reason, so we do not have a unique solution. The reason for that is that one reason for that is that we have limited acquisition at the surface and not around the Earth, so not around the body. So just at the surface, so we just have a limited view of what we could see. So a way to simplify this, here in that case, is to explain this kind of data here we would probably have to find a model similar to this, and we would have to propagate waves in this kind of model. So we need finite difference or finite element codes to simulate the propagation in a given model. So to simplify the determination of the optimal model, optimal velocity model, we one possibility, one classical possibility is to split the model, so that model, into different parts between the low frequency part and the high frequency part. So the high frequency part contains singularities, so what we call reflectivity or scattering part, and the low frequency part contains the long wavelength of the model. Determination of this high frequency part, singularity, or another name is reflectivity, is done by migration, and I explain in a minute what I mean by migration. So seismic migration means we would like to determine the optimal reflectivity part, singularity part. And the low frequency part is important, and this is what we usually call tomography. So not necessarily term tomography, but tomography in a broad sense. So this term is a bit bizarre, but okay, it's this tomography. And basically we split these two using mainly the Born approximation. So we do not have to do that, but it's an easy way to split this model into two parts. So here is an illustration of the reflectivity part, so the singularity part. So this is an image after processing, after what we would say migration, seismic migration, where we have a final image of the discontinuities. So this is vertical axis and this is horizontal axis. And we do get an image that should be interpreted. So you could see horizons, okay, like this. You could see discontinuities in horizons, maybe like this, here and here. So you have horizons, they more or less stop, and they start again a bit further away. And you have some sort of structure. On the other side, you also have, if you are a geophysicist, you can see that you have crossing events. Like you have an event like this, here, dipping like this, and another one dipping in the other direction. And this is not really geological image. People do not really like crossing events. So what is the reason for that? In fact, to build that image, we have to know the mean or the long wavelength velocity model. And here I took non-optimal velocity model. That's why this image is maybe not too bad, but in fact it's a defocused image. So if I take the correct image, then I got this kind of image. Okay, this is the same input data, but migrated, so with another velocity model, with another velocity speed. So in the human body, normally you have a water velocity. Here, in Earth imaging, you may have velocities between, let's say, 1500 meters per second to 6 kilometers per second. And you may also have lower velocities in the case of unconsolidated sands. So basically you have a ratio, possible ratio, between 1 to 10, between 500 meters per second to 5 kilometers per second. And we need to determine this optimal background velocity model, the optimal smooth velocity model. So in that talk, I'm mainly going to concentrate how to determine this model. But first of all, I'm going to explain a bit more how to determine that reflectivity part. Okay? But keep in mind that the smooth model has a large influence on the final result. So this is with an incorrect background model and with a better background model. Okay, so as I mentioned, an easy way is to split the model into two parts using a Born approximation. So here's a model, so VP, let's say, pressure wave velocity model, split into the background model and the perturbation. And for the data, for the input data, we also split into two parts. So usually, M0 is a smooth model, so it's non-reflecting model. So this is how we split the data into two parts. The reflection part is associated to this, and the non-reflection part is associated to to the smooth model. So what is the non-reflection part is basically transmitted waves propagating around the surface, sometimes a bit more complicated, but mainly transmitted wave. Okay, so P solution here of the wave equation. So here I put the classical, simplest acoustic constant density wave equation with a given velocity here, and P naught, here is solution of the same wave equation, except that here we work with the background wave equation, background velocity model. So how to determine the optimal reflectivity part, so the singularity part. So it's an ill-posed problem, so we need some regularization. So we set as an inverse problem with a L2 norm, and basically we try to minimize the misfit between observed data, perturbed observed data, and perturbed computed data. Okay, and it appears, thanks to the Born approximation, that this is a linear problem, that the perturbed data here, so this perturbed data linearly depends on the perturbation, on the high frequency perturbation, on the reflectivity. So this is an inverse problem, and we more or less have this kind of solution with regularization. Yes? P?
B.
B.
On the right hand side there.
Oh, yeah, here. So this is the differences between observed data and computed data. And here would be with different notation. Here I wanted to underline that delta P is a linear function of delta M we're looking for. So B is observations, and A delta M is simply delta P. I just wanted to say, okay, we have to solve A x is equal to B. Okay. So B is the observations. Okay, so we need some regularization, and formally, just formally, we have the optimal reflectivity function of this. But in practice, we do not do that. In practice, we do something much simpler. In practice, we simply take the adjoint of the modeling operator. So instead of having this optimal reflectivity part, we simply take the adjoint. Okay? So A is a modeling operator, B is the adjoint, it's what we call migration operator, B are the residuals, and we simply apply this. So I put this name, Lai and Tarantula, because what people did in the past is that they applied this formula. And these two people recognize that this formula is a gradient of this objective function with respect to delta M, taken at delta M is equal to 0. We don't know anything, so we suppose at the beginning that delta M is 0. We compute the first gradient. So this is the first gradient, and this is the optimal result. What is the effect? In fact, that solution is not too bad. So let's give an example. So suppose I have some data, and then I compute the misfit data. So initially, I would like to find the optimal delta M. Here, this is my initial delta M. So I don't know anything, so I put delta M equal to 0. If delta M is equal to 0, then my reconstructed data is also 0. It's linear. Okay? So then I have a large misfit. Misfit is the difference between reconstructed data and observed data. So this is minus observed data. Then I compute the first gradient, and I obtain this kind of image. I make a zoom in a minute. Then the reconstructed data associated here to a scatter point would be this data, and the misfit is lower and similar to this. And then I could iterate and I end up with this kind of model, and the misfit becomes much smaller. And my reconstructed data is very similar to my observed data. So in the middle, I only applied the adjoint, so this, and on the right, here, on the right, I solved this equation. In fact, instead of having this formulation, I iteratively solve this equation. So let's have a look at a zoom. So this is my reconstructed data after one iteration, and here after 20 iterations. And what I mean is not too bad. It means in terms of kinematic, I was able to find the position of the scatter here in the middle. And here, this is the position of the scatter, and same position. So that's not too bad. But of course, I have here better resolution. So I have better vertical resolution and better lateral resolution. So what is the effect of iterating? First, you have an effect on amplitudes. Okay, I have higher amplitudes, but you also deconvolve, more or less, deconvolve the source, deconvolve the result by the source. So you have a higher resolution. But when you hear about migration, seismic migration, most of the time this is one iteration and not necessarily a number of iterations. So.
The wave operator, A transpose A is mostly identity or as a very crude approximation. Why do you have the singularity should be in the right place after backpropagating information?
Yeah, exactly. But in fact, A transpose A is not identity. A transpose A contains a source. What do I mean by source is a seismic source. In fact, we work with limited frequencies. So I need to go back to this equation. Okay, this is an acoustic constant density wave equation. And here we have, this is for a single source, located usually around the surface. And here we have what I call a seismic source. And this is a band-limited frequency source. So basically we work with frequencies in the oil and gas industry between 5 to 100 hertz. So we do not have anything above, let's say, 100 hertz. If we would have so, then it would be more or less an identity. Also, we have to compensate for amplitude decay. So we have a geometrical spreading decay, more or less. So, and in the Hessian, in the A transpose A, it also compensates for that. And finally, but I explain it later, the A transpose A also compensates for illumination and uneven illumination. We have a limited acquisition, so we have artifacts at the border, at the edge. Okay? But I come back to that. So here, the main reason why we have a better focusing is that we take that one into account. Okay, so skip this one. So here I'm interested in how to determine the background velocity model. So this is what, and among different possibilities, I would like to give something about migration velocity analysis. So what is the principle of that? We have seen that you could get an image knowing a given background velocity model. We could test migration in different models, in different background models. One would give this, and one would give this. The idea is that we could have a subset of the data, or we could migrate data in different kinds, and if we have consistent images, then we say, okay, this is a correct model. If we have inconsistent images, then this is an inaccurate model, and we have to update. So, yet it's a bit obscure, but I'm going to give more insight. So, but basically, the principle of migration velocity analysis is that we compute different migrated images, and they all should be consistent if we have a correct background model. And if they are not consistent, then we have to update that model. So how to measure the consistency of different images? Well, there are a number of possibilities. So, and I explain one possibility. So here, if I go back to the Born approximation, how to model the perturbed data with the initial velocity perturbation, I introduce a G0, that is green functions, and here this is between the source to the image point, and here between the image point to the receiver. So here we suppose that we deal with a single first order Born scattering approximation. So where we have a source, wave reflects somewhere only once and back to the receiver. So that's why we have two green functions. And in the middle, we have velocity perturbation, or what I call reflectivity. So psi is now the reflectivity. And here, that is important, we have the source term in frequency domain. So what we could observe is that we have input data, let's say in 2D, depending on a source position, receiver position, and time, or frequency. So it's in R3, okay? And here, what is our reflectivity? It depends on the depth position, X and Z. So it's in R2, okay? So if we would like to reconstruct this from this, we have redundancy, and we will try to benefit from it. But if we would like to establish a link and to be able to go back and forth between perturbed data, so delta P, and reflectivity, then we have to go back between a 2D space and a 3D space. So on one way it's possible, but on the other way it's not possible. How to go from R2 to R3. So that's why people have proposed to extend the size of the model. Instead of having a reflectivity depending on just X, so X and Z, they have proposed to put an additional term that is H, and that is some sort of offset. So, for example, James Rickert is here and has worked on that. So, the reason for that, so H is a scalar here in 2D, so, and this is so that the reflectivity is defined in a space, in a 3D space, that has the same dimension as the input data. So we may hope to have a way with a joint or with a forward operator to go back and forth and to possibly iterate. Okay, so what is this? So suppose we have the source here, we have the receiver here, and we have the image point. If you have a correct velocity model, then you may expect to have an image here. But if you have an incorrect velocity model, well, you will be also creating images corresponding to non-physical path, to non-physical imaging condition. That is, you will see, okay, maybe my time is too long, so why not creating a shorter path with this time, with this offset, such as I may create artificial images at non-physical points. It's a bit bizarre. If I have the correct model, then all my energy is going to focus at X for different sources, different receivers. If I have an incorrect model, then I artificially create points and I apply my imaging condition, but at two different points. Normally they should be at the same. And here I created at two different points, such as I still have some energy, and I know, okay, they do not focus at the same point, so this is an indication that my model is incorrect. So you see, it's quite strange. So we need to solve two inverse problems. One is, first, in a given background velocity model, we need to find the optimal reflectivity function of space position and function of possibly of the offset. Once we have this optimal reflectivity, then we try to minimize that function. So what is this function? So A of H is the norm of H. Okay. So if I have the correct model, then my energy is going to focus for H equal to 0. For H equal to 0, this is a physical point. So my energy is going to focus here. So then I multiply by H. So I expect this quantity to be small. If I have an incorrect model, then part of the energy is going to focus at a non-physical position. So I will have energy at H non-equal to 0. So I expect to have a non-zero here. So I would like to minimize this function. Okay? So one way, and this is one way to determine the optimal background velocity model, is to minimize that function, knowing that this quantity is solution of this inverse problem. So here is a linear problem, as I mentioned at the beginning, and here it's a nonlinear problem. Okay, So I would like to, so we do have an explicit formulation for the extended reflectivity, and I would like to compare two approaches. One is, let's say, the correct approach. Correct approach is we would like to find the optimal reflectivity. So probably we need to do iterations, or we have to invert for the Hessian, for the inverse of the Hessian, and put that optimal reflectivity here. So this is solution number 2. This is what I meant by quantitative migration. So psi is the solution of 1. Or, as I said at the beginning, migration could be only the first gradient of this. So we simply take the joint part. And I would like to compare what happens if I take psi not solution of this, but a good guess, first iteration. Okay? And I would like to show some examples that if you do the second approach, then you have a better behaved objective function. And if you take the first one, okay, it's much faster. This is what we do in practice. Then we have a less behaved objective function. So my message is, through very simple examples, if you properly solve that equation through some regularization, then you have a better behaved objective function to determine the background velocity model. So it's worthwhile to spend some time on this one. Okay, so now I give you some examples, but before I reviewed a bit, people have proposed to properly solve this equation, and they call it quantitative migration or iterative migration. Okay, and in different contexts. First context is for sparse acquisition, where you have a number of receivers, but you only have a few sources. Okay, especially in 3D, so you only have a few sources. So if you don't do anything, you have a number of artifacts. So if you do migration, iterative migration, you have a way to regularize the problem. So this was for how to deal with the sparse acquisition. People, as a bit before, also use quantitative migration, so to have a more quantitative reflectivity and to have a better resolution. This is exactly what I've shown at the beginning. So you properly solve that, and you have a better focusing. Okay, and here we propose. So people have also done that for attenuation. We propose to have quantitative migration, and the objective would be to improve velocity estimation. So would be to improve the shape of that objective function. So let me give you what I think, but this should be further analyzed. What I think is a crucial element in that analysis. If you analyze the Hessian, as you mentioned before, you have different, the application of the Hessian has different effects. One is about amplitudes, okay, to correct for the geometrical spreading. So if I modify my amplitudes, basically my scheme, my velocity estimation scheme does not change much, or you could compensate for amplitude, but this is not the main effect. If you deconvolve by the source, okay, you have better resolution on magnetic image, but here I'm looking for a smooth background velocity model, so probably it has an impact, but I think it's a limited impact, okay? So this is not the main impact. The main impact is about compensation for illumination. So what do I mean by compensation for illumination? We have sources and receiver at the surface with limited acquisition, with limited what we say offsets, so distance between sources and receivers. So, and sometimes we have sources and receiver within the well, but here, okay, I put just sources and receiver at the surface. Then we have a propagation, a model, let's say non-homogeneous model, and wave propagates within the Earth. So at the image point, we do not have an even illumination. We have an uneven illumination. So, and the Hessian, if you properly apply, one effect is to compensate for illumination at the image point. We may have a regular acquisition. It does not mean we have a regular illumination at the image point, because of limited acquisition and because of a non-homogeneous velocity model. But this is This is, I think, the most important thing. So one way, but there are different ways, is to modify the objective function. So the top one, here, this is top one, and to introduce a weight such that the Hessian becomes more or less a diagonal. So up to smoothing terms, okay? To do that, we did that within the high frequency approximation. So not necessary to compute this, but to compute that term. And what happens is that, so we have amplitude terms, we have deconvolution terms, and so on, but there is a key term appearing that is a Belkin determinant. I'm not sure maybe you know that. What is a Belkin determinant is a way to say what happens between my local coordinate at the image point and the coordinate at the surface. So this is to compensate for illumination. So what are these vectors? They are vectors at the image point. So here we work in the extended model science. It's a bit bizarre because we do not have the same point, but basically if you work with rays, the Q is the sum of these two vectors, slowness vector at the image point, and multiplied by the frequency, angular frequency, and H, you have KH, that is the wave number associated to H. Okay, so details are not important. The only important thing is that if we implement that determinant, that in principle should be there, then we will mainly compensate for illumination. And this has the main effect on velocity estimation. Okay, so now there is no more equation, just a few illustrations for the next 5 minutes. Here's an example, a very simple example, where I have a flat interface embedded in a homogeneous model. And here are the extended reflectivity. So this is function of depth here. So normally it's a 3D, but I took a section for a given x. And here, this is a h. So normally for the correct model, my energy should focus at h equal to 0. Here on the left, I took an incorrect velocity model, so a velocity too slow velocity model. Here more or less the correct velocity model, and here a too high velocity model. So you see that most of the energy here collapse at h equal to 0, meaning that I expect to have a correct velocity model. But on the other side, you also have this kind of artifacts. Okay, why are they? Basically, you have limited acquisitions, so you have truncations. So even if you taper a bit, you have this kind of the artifacts. So you could do some processing to avoid them, and this is what I think people do. But especially for very shallow targets, so he's only 200 meter depth with some large offsets, you have this kind of artifacts. So if you taper a bit, so if you play with data and you avoid truncation, then you have a better image. And when you apply, in fact it's not really visible on the screen. If you apply the weight, you have something even better. So I just flip back and forth, where you have this or this, okay? So one is, let's say, without application of the Belkin determinant, and the other one is with the application. Okay, so in that case, you know that the artifacts are more or less what we call smiles, okay, in that sense. So you could maybe here remove based on curvature, but this is not what we would like to have, because here we have the same curvature, so it would be difficult to split them between the two. So what is the effect? Well, here I display the objective function for different velocity values, just homogeneous velocity values. So which I display the second objective function, and psi has been determined either with first iteration or with many iterations. Okay. So with only one iteration, we got an objective function that is similar to this, with a dashed line, and with playing with the tapers, as the geophysicists do, then we improve that objective function, and we have the dotted line. And by simply implementing the Belkin determinant here we have a more quadratic objective function. And also the minimum has been shifted towards the correct velocity model, velocity value. Okay. So here, if my message is simple, if you correctly solve for the migration inverse problem, then you have a better shaped objective function. And what about the gradient? Here we have a single interface, so you would like to update the velocity model. But what happens in this part? In this part, go back to these images. Let's say here, we have the interesting energy that is here. And also we have artifacts on the edge. So if this is really true information, it means that at large offsets, we have non-zero energy. So it means that we have to update our velocity model. So there is a large update in this part. And here, there is basically no update because energy is concentrated at h equal to 0. And that's why, for example, in this case, that the gradient, so my velocity update, has large values. And if you have the correct weight, you have a much even velocity velocity update. Here we have artifacts on the edge, okay, because here we have limited acquisition. But here that part should be extended. Okay, so just another more complex example, but similar example where we work with this more difficult data set. And still we have a shallow target at a few hundred meters, and here we have 5 kilometers long. So that model should be really extended like this. Okay, it's a very shallow target. And we do have exactly the same kind of effect. So here there are what we call extended reflectivity, function of depth and function of offset. And here with the weight, and here without the weight. So you see the difference. Most of the energy is for short offsets, so the effect is not too large. But if you go with too high velocity, then you see that you have about the same curvature, but you have effect on this. Okay, so we do have about the same conclusion about the gradient. So yeah, here it's a bit difficult to see. Basically, you have to compare this image and this image. Okay, you have deeper penetration zone, but on this one it's a bit more oscillating. Here in this part, you would have, if you look on the screen, you would have some blue. So if you enlarge a bit, you would have some sort of oscillatory gradient, whereas here you have a more even gradient. So that gradient has been obtained with a velocity that is too slow. So we expect only blue values, and here we expect only red values because the initial model was too high. So there are more complicated things here, but I skip that part. Okay, so conclusion. Conclusion is that migration velocity analysis is a classical technique based on redundancy of data and based on you need to migrate data set a number of times. And this data set or these different images should be consistent in one way or another. One consistency here that they should focus at extended offset, so at h equal to 0 for the correct model, and otherwise they defocus. And for migration, you have plenty of possibilities. One is to apply the classical migration that usually geophysicists do, so just the first gradient of the objective function. Or you could also iterate, so you have to pay. It's much more expensive, okay? But this is an automatic way, what I think, it's an automatic way to consider, to compensate for elimination. And people have proposed other ways to compensate for elimination. It's more where you really have to introduce some picking or some a priori information, and basically it has the same kind of effect, okay? And here, solution is more automatic way. Okay, so we work on, for migration, it's inexpensive, so here we had a possibility to apply just one iteration by simplifying the Hessian, but it's only done with a high frequency approximation. So we work on iterative solvers to have a fast and efficient migration for later more robust velocity estimation. Okay, so that concludes my talk, and thank you.
Thank you. We have a few minutes for questions. just to be clear, you're inverting for only the migration velocity model, or the migration velocity model and the background model?
So in fact, I'm inverting for both.
Okay.
Yeah,
So
but
when you talk about nonlinear iterations on that last slide,
yeah. So in fact, I do it iteratively. So first, at the beginning, I need to suppose I have some background velocity model. So suppose homogeneous background velocity model at 1500 meter per second, water velocity. Okay. Then in that image, I'm computing my reflectivity, optimal reflectivity or reflectivity.
Okay.
And then from that, I update my velocity model, my background velocity model. In that new background velocity model, just one iteration, nonlinear iteration, I still have to recompute the extended reflectivity and once more. Okay. So this is For the background velocity model, I need an iterative process, typically with a steepest descent or conjugate gradient or quasi-Newton, whatever. But indeed, this is an iterative process where at each nonlinear iteration, so at each iteration where I update the background velocity model, I have to remigrate, so redetermine my optimal reflectivity. Why? This is a reason at the beginning. If you change your background velocity model, you will flip between this and this, between intermediate solution. But the migrated result really depends on the background model. Background model has an influence on the kinematic of the wave propagation.
Yes, how do you separate the fast and slow scales that you reconstruct, and do you use that separation as a sanity check somewhere in your calculations? If the gradients that you get for the smooth part are too big, that probably means that you did a bad job in separating the frequencies. Is there a reasonable understanding of how you can separate them, how well it works?
No, it's very ambiguous. It's very ambiguous. So what? So two things. First. When we do the nonlinear iteration to update the background velocity model, most of the time we project on some, let's say, B-splines. So because of that parameterization, we have only a smooth model. But you do not have to project. You could use a regular grid. And so people have seen that when they iterate for the determination of the background velocity model, at some point, after a few iterations, they also come up with high frequencies, with singularities. That is not at all consistent with the hypothesis at the beginning. And in fact, they don't know if they have to stop because it's not consistent, or if they could go a bit further away. Because here they mix different structures. So there is no answer, I think.
So in practice, are the high frequencies 100 hertz and the low frequency close to 1 hertz? And is there some place where you?
Yeah. So in fact, on the data side, Claerbout, with a professor at Stanford University, famous geophysicist, drew a picture, a cartoon, saying that my intermediate frequencies in the velocity model, data is insensitive to intermediate frequencies in the velocity model. So this is really the Born approximation of what we have in mind. And this is why people say, okay, either I have the high frequency part or the low frequency part. Okay. What happens now is that instead of splitting into two parts, background and reflectivity, now people try to have a uniform, not uniform, but a single minimization. And basically they start from low frequencies because it's a very nonlinear problem. So they start from low frequencies, they increase the frequency content of the data. By increasing the frequency content of the data, they are able to increase the resolution in the model, and they go from low to high frequencies. And in that case, they do not have to rely on the Born approximation.
You cannot get the low frequencies if you don't have the high frequencies, because they need to reflect.
Yeah.
Get any signal, so that's
yeah.
Work, right?
So exactly. So in that case, people use different kind of waves. So you have the reflected wave. Okay, they need to reflect, so you need singularities. Okay. So, but also you could use a transmitted wave. So more or less transmitted waves, they propagate along the surface. But if you have a velocity model increasing with depth, we have a transmitted waves that could go back. So what we call diving waves, okay, like this. And that you have a possibility to update the low frequency part. So in practice, I do not have them because I just remove them. So there are some processing applied on the data.